So now let's look at what's happening with two variables. Well, you know it, you guessed it. We need to have, if we want some extreme values, so if we've got two variables, you have a surface that looks locally like this. If you've got looking at a minimum, or a surface that looks locally like that, if you're looking for a maximum. Okay, and we have the same idea. If you are restricting to one direction, let's say that this is the x direction and that would be the y direction. It looks like a minimum for both directions. Here it would look like a maximum for both directions, x or y. Okay, so what we need, all the partial derivatives are equal to 0. Okay, so it's really the same thing, because if we cut and look at the partial function, we need the partial derivative to cancel out, because it corresponds to a minimum or a maximum of the partial function. So we need to have a critical point. Okay, that's a necessary condition for optimum. Okay, so what does it look like? That's my necessary condition. That's what we said, local mean, local max. And we still have something that may happen. We may have something that looks like a maximum in one direction and a minimum in the other. And so maybe I'm not going to try to draw that horse again, but this is a saddle point. Okay, so that's like the saddle of a horse. This is what is called this point that corresponds to a maximum in one direction and a minimum in another direction. That's called a saddle point. Okay, so these are the three cases. So let's sum up. Necessary condition for optimality, we need a critical point, but once we have a critical point, we don't know yet in which case we are. We could have a local minimum, a local max, or a saddle point. And again, same idea, we need to discriminate between those. And what do? We're going to look at the second order derivative. Okay, so necessary condition, the gradient is equal to 0. We could have one of those three cases. What's happening? First thing, let's say that you've got a critical point x star y star. Here we have rewritten the second order Taylor expansion. What's happening there? Okay, let's say that you've got a minimum value or a maximum value, whatever. Doesn't matter for the moment. It means that it corresponds to a critical point. Critical point, the gradient of your function is equal to 0. Gradient of your function equal to 0, it means that this partial derivative is equal to 0 and this partial derivative is equal to 0. So that this, that's going to be the next slide. If I do the difference f of xy minus f of x star y star, this is cancelling. And we only have this. So that if I want to know the sign of f of xy minus f of x star y star, do we have that this value is positive, so that this would be a minimum? X star y star corresponds to a minimum. If this is smaller than 0, that would be a maximum. And if it's not always the same sign, well, we would have a saddle point. Okay, so I need to determine the sign of this stuff. So that's the Monge criteria that you learned last year. So we have, and in year 1, we have that this thing is about, well, so the gradient part is equal to 0. So we only have the order 2 term, and then the small o makes that the sign of this expression is going to be the same as the sign of that second order term. One way to study that is to use these notations, call that R, call that S, and call that T. We really have something like and so we define, so H would be this stuff, that's HK, and that would be K square, K, so that's H square. So we have H square R plus 2HK S plus K square. Okay, so if I use those notations, this is what we get. Let's divide by k square, because if I want the sign of this expression, if I divide by a positive value, that's going to be the same thing. And so now I've got something looking like, sorry, k squared t, I forgot the t. We really have something that looks like, if I put that this is lambda squared, that's then hk over k squared, that's h over k, that's going to be lambda, and that's going to be 1. So I really have that or lambda squared plus 2 s lambda plus t. And I'm looking for the sign of this polynomial in lambda. Okay, does it always have the same sign, whatever the value of lambda? I remind you that lambda here denotes the ratio between the two increases in the x direction and in the y direction. So that's x minus x0, sorry, minus x0, and that's y minus y0. So does it have always the same sign, this polynomial, whatever the value of this ratio, or does it depend? Does it depend? Okay, so this is what we're looking for. So that's why we're making the discriminant of this polynomial. So 4s squared minus 4 rt, and this is going to be, well, 4 times s squared minus rt, so that you learned Monge criteria. That is, you're looking at this ratio, at this discriminant, and if ever this discriminant is negative, then you know that it never cancels, okay? Your polynomial here never cancels, so it means that it's either always positive or always negative. So you're going to have something that is either a minimum or a maximum, and we can very easily define that if the first r is positive, then you've got, well, if r is positive, then the t is also positive if you've got the same sign, if you've got a negative sign. Otherwise it wouldn't make something negative here because of that. So if either r or t is greater than 0, they should have the same sign again. In the case where it's negative, then you've got a minimum, and if it's negative, you've got a maximum. If your delta is greater than 0, it means that you have a polynomial that changes sign. Sometimes it's positive, sometimes it's negative. So that means that it depends on the ratio between h and k, between the kind of increase we're doing in the x direction and in the y direction. So we would have something that is not independent of the surrounding of the neighborhood that we are traveling in. Okay, so that's the Monge criteria that you learned last year. Actually, this year I would like us to use something, the thing with this criteria is that if I go up to more dimensions than 2, that's not going to be something that I can apply. So we need some more condition when we want to do optimization with n variables.